Thank you, Fritz. So I'm sorry that I can't be here personally, but honestly, I was a bit scared with all these cases that recently emerged. So anyhow, I tried to give this talk now online. It's actually the first time I give a talk online. So usually I completely refused. So we'll see whether this works out. So the topic that I would like to present to you is integer optimization with a view towards high dimensions. So this is very general. And in fact, what I would like to look at is now the classical integer programming problem. So we maximize a linear objective and assume x is in a polyhedron intersected with the integer points. And I will refer to two types of polyhedral representations. So on the one hand, it's all classic inequality representations. Here, I typically assume that A is integral and also that the right-hand side vector is integral. And I will comment on this. This, in fact, makes a difference. And the second type of polyhedra that we occasionally will look at is standard form representations. So then here we assume x is non-negative, and we have a bunch of equations, ax equals b, and assume that A is a full row rank. So I guess this is all known. But now what I would like to look at is this integer optimization problem under the assumption that n is very big. So what can we do there? So what I would like to give you an impression about, and in fact, occasionally only a glimpse, is on two specific topics that I think nicely fit into this framework. So on the one hand, we want to investigate the family of all high-dimensional integer programs that share a common fixed data parameter. So the parameter I will typically look at is delta, which is the maximum of the absolute values of all subdeterminants in the matrix A. And for this here, I will refer also to this notation, totally delta modularity. So once again, we now fix delta. Delta is maybe 3 or 4 or 5. And now we let n go. So the second type of problem is really very orthogonal, and I will very briefly comment on this in the next couple of slides. This is to identify sparsity patterns in a matrix A that allow us to solve high-dimensional problems via smaller ones. So these are the two types of topics that I would like to present today and give you an impression why this is maybe in certain parts exciting. Is that so far clear? So these two topics, A and B, on the first glance look very, very different, but they do have something in common when we imagine that the dimension is huge. And the first thing is, I would like to comment that A and B really act on very different levels. So A obviously does not impose any obvious geometric structure. So when we fix the maximum subdeterminant within a matrix A, then clearly by Laplace expansion, one can see that the set of all these totally delta matrices, they define a semi-algebraic set. And this semi-algebraic set has some structure, certainly, but this structure is not very well understood. And even basic properties like, is this semi-algebraic set connected or so, all these things still remain pretty much unexplored.
But so, this is not integer, right? So just real.
Yeah, so the set of all totally delta matrices, this would first be a real semi-algebraic set, but then of course we are interested in the integer points in the semi-algebraic set. Yeah, absolutely. So why do A and B act on different levels? Well, this is very simple. Imagine I give you some sparsity pattern in a matrix. So for instance, the matrix A as indicated here. So we have these matrices C1, C2 up to Cn. This is, so to say, the common intersection. We do have a few columns, 0, B1, B2 up to Bn, that intersect with all other entries. And then we have these orthogonal blocks, A1, A2 up to An, and the rest is filled with zeros. So this is clearly a sparsity matrix. So in fact, this is called a 3-block matrix. But as you can imagine, even if the little blocks AI have a small subdeterminant, then of course this matrix A has a gigantic subdeterminant because it's in the order of delta to the n, if delta is the maximum subdeterminant of a small matrix AI. I guess this is clear to everyone. And so A and B really act on very different levels. And both aspects, I think, are interesting in this context of having n as a parameter, which is now assumed to be very large. So is that so far clear? That's the type of problems we would like to look at. So yeah, this is always the problem with these online talks. I can see a few of you in the audience.
We are nodding. So if there's a question, we will yeah.
Okay, good. So now the way I would like to continue the talk is I start with this topic A, and then we go to topic B, and at the end I will comment a little bit more about this intersection of the two. So concretely, when we look at this questions of type A, so now again, we have this fixed data parameter, which is our determinant value for the absolute value of all the subdeterminants. And then every instance now of IP is parameterized by n, by m. So n is the dimension, m is the number of constraints, and delta is this parameter. And now we want to understand functions, and the function value is indeed the worst case, or it can be the average case, among all instances of input n, m, and delta. And the key questions that we would like to address are functions of the following form. So in particular of relevance here are the following four functions. Proximity function. So proximity, this is really at the core. In fact, proximity asks for a bound on how far LP optimal solutions and IP optimal solutions are away from each other. Sparsity makes particularly sense in the case of a standard form IP. So again, standard form means you have equations AX equal B, you have non-negativity on the variables, and now you ask yourself, given an optimal integer solution, how sparse is this solution? So how many non-zero entries do we have? Another super interesting parameter in this context is the lattice width. So the lattice width asks, given this polyhedron and assuming that there's no integer point in the polyhedron, then can we find a flat direction? So in a flat direction, which ideally is now depending on delta and not so much on n. And finally, the running time function, that's pretty obvious. That's just the time it requires to solve such an optimal solution. So as a very brief example, I mentioned this already. Very briefly. So imagine a polyhedron has no integer point. Then what we know from Kinchina's theorem is there exists an integral vector d different from 0, such that if I now slice the polyhedron according to to this normal vector d, so in other words, I look at the maximum of dtx over the points in P minus the minimum of dtx x in P, then this is bounded by a function which entirely and only depends on n. And so the question here is now, given that I now want to imagine that n is very, very big, but can we find a flat direction whose width is bounded solidly by delta? This would be the dream. And in fact, it is not so difficult, but very beautiful. There is a beautiful connection between proximity and lattice width. So if you can prove such a statement for proximity, then you can also prove such a statement for the lattice width. I will not comment on this further, but this is some work in progress. I anyhow find it interesting that on the first glance, these functions have nothing to do with each other, but at the end, in fact, there is some relationship between them. So now, what do we know and why could it make sense to address this issue with small values of delta? Well, the first thing is there's the theory of totally unimodular matrices that emerged in the past 50, 60 years. And it's really the foundations of the field stem from results for delta equals 1. So delta equals 1 is the case to start with. And we do have established a very nice theory of TO matrices within the years 1950s to 1980s. In particular, in the context of integer optimization, we all know from Hoffman and Kruskal's theorem that IPs can be solved as LPs, simply because we assume that the right-hand side is always integral. And then the LP optimal solutions happen to be integral, which is a fantastic property. And of course, we know much more about this theory of totally unimodular matrices. We have in particular CMOS decomposition theorem at hand, and we have a polynomial recognition algorithm so that we can say, given a matrix A, can you recognize whether it's TU or not? So there's a huge machinery, deep, beautiful, with connections to all kinds of fields, matrix theory, combinatorics. And so the question is, can you really extend this theory a little further? So when delta is equal to 2, now many things have been established. In particular, there's this very foundational paper by Veselov and Cherkov that I would like to mention in this context, that I think one can argue that this really explains the geometry for delta equals 2. So in particular, one of their strongest results is that if you assume that the given polyhedron in inequality form, ax less or equal to b, is full dimensional, then you do have the property that LP feasibility implies IP feasibility. So what this in particular shows you is when delta is equal to 2, and now you assume that the polyhedron does not contain an integer point, then the logical consequence is that this has to lie on a hyperplane. So in other words, there's a flat direction of width 0. And accordingly, we now also know how to solve the corresponding optimization problem when delta is equal to 2 in polytime. And this is some joint work with Stefan Artmann and Rico. So there are many more things we know about delta equals 2, but I think these are two of the major important things that I would like to share with you. Unfortunately, this is already pretty much the end of my story about what we know when delta attains some small values. And in fact, we have spent some time on understanding delta equals 3. I'm still optimistic we will at some point see what to do there, but it's much more complicated, even when delta is 3. So that's still a lot of work. But now I would like to comment really on what I think is one of the key functions when we now assume that delta is small. And this is now the function related to proximity. So the point of departure is this theorem by Cook, Sheratz, Schreiber, and Tadeusz from 1986, which can be stated as follows. So assume that A is totally delta modular. So all subdeterminants have an absolute value of at most delta. Then for an optimum solution X star of the linear programming relaxation, there always exists an optimal integral solution Z star for the corresponding IP with a property that in the infinity norm, X star and Z star deviate by no more than n times delta. So this is a key result, but you see, the thing is here, in view of very high dimensions, we only have the linear dependence on n, and we have a dependence on delta, but ideally we would like to get rid of this little n. So that's the kind of task that we have. Now, I thought during my talk, I only tried to convey the things which I regard as elegant, and I will push many of the technicalities under the rug just to give you a glimpse of what happens. Now, this is one of the results which you can state in, and also the proof that you can really give on one slide, and that's why we are going to do this. It's a 4-line proof where I left out a few little details that one can check. So how do we get this bound of n times delta? So the proof idea is you look at this difference vector, z star minus x star. And what you know is this vector lies in a cone, and the cone is defined by the given inequalities of our matrix A. And now for a subset of them, you know that the difference vector is less or equal to 0. And for the complementary subset, you know that AJY is greater or equal to 0. So this defines a polyhedral cone. And in fact, now take this cone and consider the inner description of the cone. So U1 to UT are now scaled extreme rays and scaled in a way that all entries are integral. Yeah? Good. So now, the second thing is, for every index I, so for every extreme ray, we already commented, so the UI was scaled to be integral. It is very simple to see that CTUI is less or equal to 0. And that has to do with the fact that you start off with X star. And this is the optimum LP solution. So if you had some positive value, some vector in the cone that is positive, then you could improve on the LP point, which you can't. So this is why we have the CTUI less or equal to 0 property. And then using linear algebra, in fact, you need Cramer's rule to establish that the norm of these extreme rays are all bounded by delta. So this is really Cramer's rule. So far, so clear? So, and the 2 more lines you need, and then you are done. Well, now we look at this difference vector, and we know we can express this difference vector by Carathéodory's theorem as a linear combination of the extreme rays, in fact, as a conic combination of the extreme rays. And we need at most n of the extreme rays to represent this difference vector. But now it's obvious that the lambda I values, so the multipliers, the conic multipliers, have to be smaller than 1. Because if they were greater or equal to 1, then you could extract an extreme ray and shortcut the difference between the LP and the IP solution. But now, given that the lambda i's are all smaller than 1, and that we only have at most n of them used in the representation, we get a bound of n. And this, together with the fact that the UI in the infinity norm are bounded by delta, gives you this bound of n times delta. It's a super elegant and somehow simple proof if you know what to do. So now, the question is now, is it really possible to improve on this proximity function? And this is a hard nut, at least for me. I've been thinking with many other people about this question for several years, and still it's somehow very, very moderate what we can offer. So the first question is it really possible to improve on the proximity function? And in fact, we have to be careful. So here is really where you need integrality now of the right-hand side. Because in general, this bound of n times delta is tight when you allow B to be fractional. So the reason is there are several examples. In particular, there's one by Lobash. He gave a TU matrix A, and then some fractional right-hand side where you can really see that the distance between IP and LP solution is in the order of n times delta. And there's another recent example by Alberto Del Pia and one of his co-authors. So we can potentially only improve if B is integral. Is this clear? So, but remember, I said in the beginning, during my talk, A is always assumed to be integral and B is assumed to be integral. So there's a little bit.
You can always round. I mean, you can round down the B, right?
Absolutely, absolutely. But in order to get, absolutely. And that's why it makes a lot of sense. So when you at least want to deal with this integer optimization problem, right up front, we can assume by rounding that the B is integral. Yeah. Absolutely. So as I told you, I opened my mouth too much. I want to arrive at a bound which is independent of the dimension. The only thing I can offer you is some recent work with Marcel Zelaya, Stefan, so Marcel is a postdoc in Zurich, Stefan Kuhlmann, he's a PhD student in Berlin, and Joe Pett, he is an assistant professor in Vancouver. So the only thing that we so far know is when n is greater or equal to 2, and A is a totally delta unimodular matrix, and B is integral, then we can improve on this Cook et al. Bound in the following. So what we can show is that given an LP solution X star, there exists a closest integer point Z star whose difference in the infinity norm is bounded by 1/2 times n times delta. So when delta is 3, we can do better, but in general, we so far can't do better. So still, we are absolutely convinced, and I'm absolutely sure that you can bound this by a function, only depending on delta. And this is the target where we would like to go to, but what I now want to do is I want to give you a glimpse of why you can at least hope for a little bit of an improvement. And the proof of this n-half delta result is really a generalization of this Cook et al. Proof. And now I would like to convey and share the main ideas with you on how to do that. And I really thought how to do this, but as I said, I want to convey the elegant things in detail and the difficult things I push under the rug. So this is now where I can very elegantly comment why when n is equal to 2, you can really prove the proximity bound should be delta and not 2 times delta. So let me explain this to you. I think you will enjoy this, at least I hope. So now we assume this is not true. So assume one of the two components, say x1 star, is bigger than delta. So what you can now do is so what I will also now assume is I will shift this integral optimal point z star, I called it z star before, I will shift it to 0, just to make my description here a little bit easier, if you allow me to make this simplification. So then what you can do is you can construct a spindle which is defined by the inequalities of this polyhedron, but now the inequalities are really shifted so that they are all as close as possible to 0 or to x star. And you can see this is now an object which has no further lattice point in it except for this integer point z star, which I assume to be 0. So that's the first step. So now we take one of my favorite theorems, Derrickless. So Derrickless theorem states when you have an integer delta and you have the property now that x1 star is greater or equal to x2 star, then we can look at the following approximation. So we look at, so now I don't see on my screen, so here. So then we know there exist integers p and q such that the q entry is not exceeding delta, but we can approximate the quotient x2 star divided by x1 star by these integers p divided by q, so that the deviation of the two values is at most 1 times q times delta in absolute value. I think this is a classical theorem that all of you know. So now with this, I claim we are essentially done. So we take this Derrickless theorem, and so what we know is in this spindle there is this LP point x star, and there's this integral point 0, and hence you can take any convex combination of the two that also has to be in the spindle. And the scaling now I would like to use is q divided by x1 star. That makes sense because x1 star is greater or equal to delta, and q is an integer which is at most delta. So this is really a coefficient which is at most 1. So this point is in the polyhedron. But remember, we assumed in this spindle, there's the only integer point is 0. So the point qp in particular, which is different from 0, will not be in the spindle. Okay.
Robert,
Yes.
Now I'm confused. So Q over x1 star is a number. Are we supposed to scale a vector by it somewhere?
Yeah, Q divided by x1 star times x star. I forgot the x star.
Okay. Yes, thank you.
Sorry. Yeah. So Q divided by x1 star is the scalar times x star. This is the point which is in this polyhedron.
Yeah.
But the point QP is not in the polyhedron. So therefore, this requires us to have an inequality which comes from the spindle, but the inequalities come really from the matrix A. So since we are in two dimension, it only has two coefficients, A1 and A2. And this point QP has to be separated from the spindle. So this gives you, on the one hand, that the point Q divided by x1 star times x star lies in the spindle. So that's the first relationship, A1Q plus A2Q divided by x1 star times x2 star is less or equal to gamma. The gamma is integral. And the point A1Q plus A2P, because A1 and A2 are integral, also has to be integral, but it has to violate the constraint. So it has to be off by at least +1 from the gamma value. Now, if you look at the two equations, then you directly see that this requires you that the coefficient A2 in absolute value has to exceed delta. And this is not possible because we assume the matrix is totally delta modular. So this is very elegant. I like this. So this is really the beauty of this. It's really Derrickless. Derrickless really tells us that's the way to do it. Unfortunately, this has no trivial extension to higher dimensions. So now comes a slide where I give you a glimpse of how we go for proving this n-half delta result. And in fact, we generalize the argument of Cook et al. And here, I will not go into the details. I just give you the highline expression. And I would also like to express my gratitude to Marcel, who drew this very nice picture that you can see now on my slide here below. So Marcel gave me this picture. So the first thing is, what I showed you for n is equal to 2, we can in fact extend this to two-dimensional polyhedra. So it's not only n equals 2, but you can take any two-dimensional phase of a polyhedron, and you also can use the same type of argument. And in fact, we can also partially extend this to three-dimensional polyhedra. And so what we now do, and this is really a technical, this is really pretty technical, what we can now do is that we identify in this spindle in high dimensions a collection of 2- and 3-dimensional polytopes whose dimensions sum to at most n, and whose union is connected and contains both this integral point z star and x star. And in fact, this is the clear generalization of the Cook et al. Argument. Because Cook et al., if you remember, we used Carathéodory's theorem. So we argued with the extreme rays. The extreme rays are just one-dimensional polyhedra, and you can peel off one after the other in an inductive manner to see that you only need n of them. And here we do exactly the same thing, but with higher dimensions. So we extract special 2- and 3-dimensional polyhedra for which we have an analysis, and then we take these results to get the n-half bound. The second step is that we need to argue that each polytope that we now extracted fits into an axis-aligned rectangular box whose side lengths are at most dimension of p divided by 2 times delta. And so here in this drawing that I got from Marcel, you see the path from z star to x star. We follow this 3-dimensional polyhedron, then comes the next 3-dimensional polyhedron, then comes a 2-dimensional polyhedron. And what we can argue is that in this 3-dimensional polyhedron, there everything fits into a box of size 3½ delta, the other one also into a box of 3½ delta, and the last step into a box of value delta. And if you sum this up, you get at most this n½ delta. This is now done by relating the side lengths of the volumes of this little polyhedra associated with A, and then in fact not use Derrickless theorem, but you use this Minkowski's convex body theorem. So if the volume is big enough, then you know there's an integer point inside it. That leads to a contradiction. So that's, in a nutshell, the idea. So I see somebody raising a hand, please.
Hi, thanks. So I wondered, as you said, there's a generalization of the proof by Cook et al. I just wondered, why do 2- and 3-dimensional polytopes occur here as generalization of 1-dimensional polytopes? That I did not see how this, where does this come from?
This comes from my first slide, because what we know is in dimension n equals 2, we only need delta as an axis length in this decomposition. So when n is equal to 3, we can only prove it's square root of 2 times delta, so which is a little less than 3/2 delta. But when n is equal to 4, 5, 6, so conceptually we could do the same thing for general dimensions, but we don't know this bound for general dimensions. We were not intelligent enough to derive it yet. So we cannot even prove when n is equal to 3. That would be the next step. When n is equal to 3, you would like to show that you can fit this into a box of size delta, but we don't have this. Does that answer your question? Partially.
Yeah, thanks for the intuition.
Okay, so this is in a nutshell. And as I said, I now push all the details under the rug. I only convey the very elegant things.
Robert?
Please.
So is there kind of a meta theorem here that says, you know, if you can prove better flatness somehow for slightly larger dimension, then you can chain it together in your argument to get a better better proximity. Sorry, a better proximity for n dimensions.
No, so in fact, what is enough? So we have a general lifting lemma that tells you, suppose in dimension 3 you could prove a bound of delta. Then in fact this applies to 3-dimensional polyhedra. Does that answer your question?
Well, I mean, I meant like somehow you sort of decompose things into chunks of size 3, but I was just wondering, like, if you could do something better for, let's say, like somehow that's on average better for 4-dimensional polyhedra, could you somehow break things up into chunks of size 4 and get?
The decomposition is very general. So you can decompose that. So we have a general construction that works for arbitrary dimensions, but we don't get the bound then. This is the thing. We can't prove delta when n is equal to 4. If we could prove for n equals 4, the bound is delta, then we would get n4 times delta. Right. So the construction is general.
Yeah, that makes sense.
Okay. So now I have been speaking for half an hour, more or less, in fact, even a little more, on this topic A. And I just wanted to give you an impression why I find this super fascinating. But there are also very interesting things according to the sparsity patterns. And I know I'm a little bit slow. It's always the same thing, but I try my best to get through what I wanted to convey. So now let me move on to this topic number B. So now from A, we go to sparsity patterns. Now, I drew here 2 matrices, and these are matrices where you can clearly see they have a sparsity pattern. So why did I draw exactly those? Because this is really not something new. Sparsity patterns have been studied for decades. And one very prominent example is, by the way, maximum ST flow over time by Ford and Fulkerson from the 50s. And this is really the picture on the left-hand side. So here, the flow has some travel time. And what this results in is that you have matrices, A1, and then with a little bit of delay, you come to A2. And then again, you have A1, that's the flow you send out at time 2, and so on and so forth. And so in general, you will get matrices of this form, A1, A2, A1, A2, and so on and so forth. So you see this has a clear sparsity pattern. Then on the right-hand side, if you look at this matrix with this C1 to Cn, D, B1 to Bn, that's the extra column, and then these individual blocks, A1 up to A capital N, this is in fact a 4-block matrix, and I gave here some references on the papers where, at least according to my knowledge, these models popped up for the first time, and where you could see that this has some polytime solvability, whatever that means. At least when you fix all data except for n. So n-fold systems, in fact, are a generalization, if you like, of multi-commodity flow, of a multi-commodity flow model, and this has been studied by Jesus, Raymond Hammack at Schmuel. Two-stage IPs, this is the special case when D equals Di equals 0, so you don't have this first bunch of lines here. You only have A1 to AN and this last column B1 to Bn. And then in general, as it is written on the right, this is a so-called 4-block IP that was introduced in Hammack, Köppe, and so on. So what is our target now? When it comes to these questions on studying sparsity. So in the context of huge dimensions, we would again like to see which IP functions are independent of the number n of blocks. And ideally, we want to have fast algorithms for solving them. And fast nowadays is FPT algorithms. So FPT stands for fixed parameter tractability algorithms. And what this means is that you are aiming at a running time, which is in the order capital N to the alpha. So n is the number of these blocks times a function that depends on a parameter k. This is what you would like to get. So now in order to tackle these kind of sparsity pattern problems, you have two types of approach. The first one, and I start with this because historically that's how it started, these are augmentation-based approaches. So in a nutshell, what do these augmentation-based approaches require? So the first thing is you need a strong bound on the norm of Graeber basis elements. In fact, you want a small bound on the Graeber basis elements because afterwards you want to design a dynamic program to compute these augmentation steps efficiently. And that's where the bound of the Graeber basis enters quite dramatically in the running time of this. And the second thing is this dynamic program is just for local augmentation, but then at the end you need a scheme that allows you to not have too many augmentation steps. And this is where typically a very beautiful theorem comes in. This is this integer Kara-Theodori theorem. So integer Kara-Theodori theorem tells you if you take a vector in a cone, and now you want to write it as a non-negative integer combination of the so-called Hilbert basis of the cone, then 2n minus 2 elements, that's the best bound by Schebel, are enough to give you such a representation. So Kara-Theodori for the linear setting gives you n. In the integer setting, we get 2n minus 2. But now you rapidly understand. So if you now manage to make huge steps with your Graeber basis and find the best augmentations iteratively, then you don't need too many steps. And then you have at the end a fast algorithm. So that's the idea in a nutshell of augmentation-based approaches. So there's another approach which is conceptually very different, but then when you can see the details, there are again similarities. So this is what I call the relaxation-based approach. So the first thing is you define a relaxation of your problem, typically in LP, but it could be something else. Then the second step is now you need to prove a proximity theorem. So the proximity theorem would tell you that if you have this relaxation point, then you find an integer optimal point not too far away. And then you design a dynamic program to compute an integer solution in the vicinity of the LP solution. And one last comment here is that if you are super smart and you want to make it as fast as possible, then you have to think about the relaxation. And occasionally it pays off to really target a relaxation towards the problem because you can prove then better proximity bounds. So are all the experts on 4 blocks and all variations in agreement that this is conceptually what you can do, augmentation-based versus relaxation-based? But you see there are similarities. Both require a dynamic program. And also very often, I would like to say this, is when you really try to prove a proximity theorem, for instance, then this goes hand in hand with proving a bound for the Graeber basis element and vice versa. So there are really similarities in the analysis. So now very briefly, I would like to mention some people that contributed important steps in this developments. And we first start with n-fold. N-fold is the special case where the right column now is set to 0. And we only have this C1, C2 up to Cn, so this overlapping constraints. And then we have A1, A2, An as the block matrices. So some people might think, this n-fold stuff is so special, but in a sense, it is not, because even the base case, so for me, the base case is when you have no blocks for the moment being. This is really the base case. But now think about the base case with upper bounds on the variables. So in standard form, I should also say that here now we always look at standard form. So we have no negativity on the variables. But now imagine you also have an upper bound. Well, this you can really bring into the form of an n-fold problem, because you just say xi plus the complement of xi is equal to ui. And so these are single block constraints of very special type. Is that clear? So there are many applications of this n-fold model in various areas, so in particular scheduling and social choice, and I listed here a list of references. And there are also extensions of this model where you study bounded dual tree depth instead of the combinatorial sparsity pattern. So some milestones, and again, it has to fit on this one slide. So the first FPT algorithm was due to Hemeke, On, and Romanchuk. And then one could remove this exponential dependence on T. T is the number of variables in the blocks AI by augmentation schemes. And here I would like to mention in particular the papers by Eisenbrand, Hunken, Schröder-Klein, by Kutetsky, Levin, and On, and by Janssen, Lasota, and Roveda. And currently one of the fastest algorithm I think is relaxation-based, and which is nearly linear in N. And this follows this relaxation-based strategy. So you set up a very strong relaxation. In fact, one where you look at integer hulls for the individual block constraints, and then you study a proximity theorem and so on and so forth. I will sketch how this works. So the second important special case when we look at these 4 block matrices is when we have a 2-stage stochastic IP. So a 2-stage stochastic IP. So now we don't have these overlapping constraints, C1 to Cn, they are all put to 0, but we have here a bunch of columns expressed through these matrices B1 to Bn, and again, our blocks A1 to An. And I find this very interesting because from my point of view, this is really a concatenation of a fixed dimension IP. This comes from these matrices B1 to Bn. So imagine this has not too many columns, so that's fixed dimension. But then you also have a one sum of that you put on top. So it's really a concatenation of fixed dimension IP and one sum. And in general, it would be very nice to have this kind of axiomatic approach. Suppose we all know we can solve IPs in fixed dimension with Lenstra's algorithm, but then if we have now an extended structure, can we somehow axiomatically extend our polytime solvability? So 2 things are solvable in polytime, and then we can do certain operations to again get to something which is polytime solvable. So this is I'm sometimes dreaming a bit too much. Anyhow, applications to stochastic IP. This is where this model really came from, where you have this 2-stage decisions. So once you have a first stage decision, this is really in these columns. When you fix these guys, then the problem decomposes. And there's also an extension of this 2-stage stochastic IP models to bounded primal tree depth, but I will not, due to Kanyan and Ordinyak, and I will not comment on this. So as we did it before, let me point to some important references when it comes to 2-stage IPs. So the first strong bound on Graeber basis elements was given by Aschenbrenner Hemeke in 07, and quite recently Klein gave a much better bound on the Graeber basis bound. So the first FPT algorithm is based on augmentation, and it's also in this paper by Kutetsky, Levin, and On, which I already mentioned. And as you can expect, the fastest algorithm is based on LP relaxation and proximity. And this algorithm still has in the parameters a double exponential dependence on the number of block columns. So AI have some columns, and so here you have a double exponential dependence. And it seems that it cannot get rid of this double exponential behavior, because there's a nice paper by Janssen, Klein, and Lasota recently that showed that this is a lower bound under this exponential time hypothesis. So does everybody know what this is? Exponential time hypothesis? It's very elegant, so I can again say this. As I said, everything that is elegant, I say. Everything which is technical, I push under the rug. So exponential time hypothesis is the assumption that you cannot solve a three-sub problem with n literals in time faster than 2 to the constant times n. So now comes the engine. How do we now go to attack these problems? And here I want to focus only on this relaxation-based approach. But I already told you the key step is the Steinitz lemma to get a proximity result. And I would very briefly like to address this. I have to watch time though, but this is one of the most beautiful things. And so let me take these 3-4 minutes to explain it to you. I know many have heard it, but still, those that heard it, you will enjoy the proof anyhow, if you get it, if you did it several times. Those that don't know it, maybe they take out something from my talk. So Steinitz lemma is the key engine. So for vectors x1 to xn in Rd, with the property that their norm xi, the norm doesn't matter, the norm is bounded by 1, and the property is that they define a zero sum, so the sum of all these vectors equals 0. We have the following property. There exists a permutation pi such that if we look at all the partial sums, so we now sum from 1 to k according to this permutation, the elements, then their value in the norm can be bounded by a constant which only depends on m. And in fact, this is really something one should teach in a basic course, I think, in LP theory. Actually, I will do this. LP techniques tell you namely that this C of m constant can be chosen to be m. And this is a beautiful proof due to Grindberg and Sebastianov from the 80s. So very briefly, how does it work? Super elegant. So it's an iterative procedure, it's constructive. So you look at sets that you now try to define. You start with the set an, this is the full set of all the elements. And then this should be a superset of an minus 1, a superset of blah, 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 up to a superset of an. This is the kind of idea. And the set ai should have a cardinality, ak should have a cardinality of k. So now we write down an LP. We write down an LP in k variables. The variables we now call lambda 1 to lambda k. And in fact, the conditions are, if I take my vectors xi, which live in Rd, the sum of the lambda I xi should be equal to 0 in the set ak.
Robert, you have a question from Sam. He wants to know what m is.
This is a thing. So this is Sam, why do you ask these embarrassing questions? You know what it is. I did it on purpose. I thought the proof is so elegant that I can do a little mistake. So sorry. So M and D are now equally taken. Okay, Sam, are you in agreement? Sam. Okay.
Yes.
Good. Thank you. Thank you. So anyhow, so now what did I say? Well, look at the constraints. So we have this M or D many constraints. Sum of the I in AK xi lambda I equals 0. The sum of the lambda I should be equal to k minus m, and the lambda should lie between 0 and 1. So now this is an LP system. And now iteratively, as long as the k is at least m plus 2, you can do the following procedure. So now you scale the solution that you have with AK in the lambdas in the way that they satisfy the equation where you replace the right-hand side k minus m by k minus m minus 1. So this scaling shows you that this corresponding system, this modified system, now where the right-hand side in the last equation goes from k minus m down to k minus m minus 1, this is feasible. So now look at an extreme point. And now a very simple analysis shows you that such an extreme point has to have the property that not all lambda I values can only attain upper bounds, but there has to be at least one such that lambda I star is equal to 0. So this is really LP theory, because you have here m equations or d equations plus an extra one that gives you m plus 1. And if you do the calculation right, most m plus 1 of the variables can be fractional, all the others have to be integral. And now it's simple to see that you cannot set the k minus m minus 1 many other variables to be equal to 1, because that would really violate the last constraint. So one of them has to be 0. That's a very pretty LP theory argument. And then you are essentially done, because now you choose ak minus 1 as the set ak, where you just drop this last index I, which happens to be 0 in this extreme point solution. And a one-line argument shows you that this gives you the bound, because if you now sum according to this permutation, j from 1 to k, then this is the same as some of the elements j and ak xj. And this is now the same as some of the j and ak 1 minus lambda j times xj, simply because you can look at this equation, some of the lambda I xi is equal to 0. So you just have added 0 in the inner part of this expression. And now you can bound this, because the xj values have a norm of at most 1. And you get that this is less or equal to the sum of the indices in AK 1 minus lambda j. And now if you look at the last equation, then the sum of the 1 minus lambda j values is precisely m. This is what the equation tells you. So this is the analysis. And I think you have to admit, this is really beautiful, isn't it?
Yes.
Good. Thank you.
In your LP class, if your students are really good, ask them if they can, as a homework exercise, if they can improve the bound by 1.
Yeah, good. Okay, so now I see I'm really too slow. Okay, so now maybe I skip this a little bit. So I thought of what can I do? So a lot of these things are quite technical when it comes to this n-fold and two-stage stochastic IPs. But I think so the key idea is really the base case. So the base case is where you have no blocks, you only have these upper linking constraints, and here I call them again A. And in fact, the key is now that you use this Steinitz lemma. That's really something that Fritz, that I did with Fritz. So the key idea is now to use this Steinitz lemma to get an improved dynamic program. And in the interest of time, I will now not explain this in detail. I thought it's also super elegant, so I could convey it, but unfortunately, I'm a bit too slow. So the key thing is, though, if I may mention this here. So the first step in getting this improved running times for a dynamic program, you get a dependence on the maximum of the right-hand sides, B, in the dynamic program, and the infinity norm of the matrix A. Now, this is not good enough for a general, in order to get to an algorithm that we could apply in order to prove a nice proximity result. In fact, what we need is, we need a bound that does not depend on the right-hand side, because the right-hand side could be huge. And so how can we handle this? Super elegantly, because Fritz told us how to do this. So in fact, you just solve the LP for this dynamic programming type approach. And then what you need, this is where the hard work lies, is now a proximity theorem. And the proximity theorem for standard form is typically where you not work with the infinity norm, but with the L1 norm. So what you would like to prove is a bound, capital L, on the proximity between an optimum LP point and the closest integer optimal point, Z star. So if you have established such a bound L, then you can proceed as follows. You now take the LP point, you have z star minus x star rounded down. So the x star point has only a few fractional components, in fact, as many as you have equations. So this is typically m. And now you solve an IP starting off from this rounded LP solution. And the LP is described by a right-hand side, which is given by this difference vector, x star minus x star rounded down. And now you see when A is small in the infinity norm, because only few components here are rounded down, the right-hand side of this dynamic program is a small right-hand side. And you update the corresponding lower and upper bounds. And you know that in total, your bound on the L1 norm is at most capital L. This is this proximity bound plus little m, and that comes from these fractional variables. And so you are back in the previous setting. So now you can apply the machinery that you know works when B is small. And that's really the key. So you go to the LP, you find a very close integer point that might not satisfy all the constraints. It might not satisfy the equations, of course, this rounding point. But then you can search in this vicinity, and that's really a key thing. And so what this explains to you, hopefully in a nutshell, even though I'm not very precise and I'm aware of this fact, but maybe it gives you an idea that you really need, in order to make this work, you really need a good proximity bound. So, and in fact, what you can now show using this type of approach is a proximity theorem for the base case. And in fact, this capital L in this algorithmic framework here can be replaced by either m times 2m plus 1 to the power of m times delta. That's in the paper with Fritz. Or there's a more recent variation of our analysis. John Lee, Joe Pat, Ingo Stallknecht, and Xing Xu, they showed that you can also get a polynomial dependence on m, but then you are a little slightly worse in the dependence on delta. So you get this extra log delta to the 1m factor. So just as examples how to arrive at this. And now I'm moving towards the end of my talk. If my watch is not wrong, then I have exactly 3 minutes. And so in these 3 minutes, I will very briefly tell you how we can extend this to the general 4-block setting. And of course, now the bounds are worse, but conceptually, I think it's very nice. So conceptually, I would like to tell you now how we proceed. So we now look at this general 4-block IP. So now we have jointly n-fold and 2-stage. So we have n blocks, and the matrices AI are S times T. We have T0 many linking variables. They are defined through these matrices B1 to Bn. And we have S0 many linking constraints. This is the number of constraints in the matrices C1 up to C capital N. So when I now write f is in OFPT of n to the alpha, then what I really mean is that the function is at most n to the power of alpha times a function of g, which depends on the parameters. So the conceptual framework is the following. Again, relaxation-based. Solve the LP relaxation. So now enumerate all integer vectors x in the space of the linking variables. So we said we have T0 many linking variables, and I claim we can now search within a small box, and the small box is really the number of integer points with a box length of n to the minimum of T0 plus 2 and S0. So what is this expression? Minimum of T0 plus 2 and S0. So once again, S0 is the number of linking constraints. T0 is the number of linking variables. So you can look at the minimum of the two values. And this, because you need to enumerate to the power of T0, gives you a bound on the number of integer points. Now, for every such point, you can now solve the problem by solving an n-fold problem and return the optimum pair x bar, y bar. So conceptually trivial. The key thing is you need this bound. And how the heck can we get to a minimum in the exponent of T0 plus 2 and S0? Well, and this is where we need an extension of this beautiful Steinitz theorem. And the extension is now an extension to multiple sequence. So the key engine here is, if you now take sequences, and in fact, you now take n sequences. N sequences, each sequence consists of m elements, ui, in a space Rd. With the following property, if you sum up over all the u's, then you know they reach a value of 0. Then you can simultaneously find permutations, not only one, but a permutation P1 and a permutation P2 up to Pn. For each of the sequences, a permutation, in other words, with the following property. When you now look at the sum, when you now look at the partial sums where you sum over all the sequences, then their infinity norm can be bounded entirely by the dimension and not by the number of sequences and the number of points in the sequence. So this is what we call a colorful version of Steinitz. And this is the key engine which allows us to show a proximity theorem. So by the way, that's joint work with Joe, Pat, and Tim Oertel. So the infinity norm between LP optimal point and IP optimum point is now in the FPT order of n to the minimum of this T0 plus 2 and S0. This is pretty hard work to arrive at this, but as I said, I only convey the elegant things, and the elegant things is really the key engine is now you have you need an extension of this Steinitz type lemma. And the same analysis also as a corollary gives you a bound on the size of the Graeber basis elements in the same order of magnitude. So you get this for free if you manage to have this colorful Steinitz theorem and you do the analysis. And so this brings me now towards the end of my talk. I know I'm now pretty unprecise at the end, but my key idea was to give you a glimpse why this all fits together. And I'm really fascinated by looking at this integer problems when I imagine in this big. Even so, I agree, I have so many more questions than answers. So where to go from here? So there are many open problems on level A: general proximity, lattice width, integer infeasibility number, etc. So the second thing which I would find interesting in this last theorem, where you get the minimum of T0 and S0 in the exponent for the dependence on n, it would be nice to get something similar, a minimum for primal and dual tree width. That would really be an extension. And I think also that it's very interesting to consider other optimization problems with the sparsity properties in B, where, for instance, you could look at subset selection in place of this linear integer optimization. And this, however, is not so easy. I thought about this also for a while. And at the very end, ultimately, maybe we can hope for combining A and B. So if we take this sparsity patterns, but now we don't assume fixed dimension somewhere in the blocks, for instance, but we assume we have now a problem where the determinant delta is equal to 2 or 3. And by then, of course, we should first understand how the problems, how the geometry is when delta is equal to 3 for integer optimization. But then maybe one could hope to combine these kind of things to get towards this more axiomatic algorithmic theory that I was mentioning as a dream in the very beginning. And for this, I hope that I was not too technical and that my talk went reasonably well. As I said, for me, it was the first talk I gave as an online talk because I always refused to do this before. I want to see the people in the audience. I want to read the faces. I want to see that Sam is now getting upset because of M and D. So I can't deliver this, but I hope it was not too boring. So thank you very much.
Thank you very much.